Good evening, everyone. Welcome to this thematic talk. I'm very pleased to meet all of you over Zoom. The topic of my talk will be on operations research. You may or may not have heard about this discipline, but it is discipline for decision making. Basically about theory and methodologies for decision making. And in it, you will see that STEM plays a big part in it, right? STEM, of course, we have been talking about this all the time in this year's science, technology, engineering, and math. This is STEM for informed decision making, right? That is operations research. And it is really both literally the STEM of informed decision making and also in terms of the acronym, science, technology, and engineering. Okay, let me start. Think about how many decisions you need to make every day, right? You may or may not be aware of it, but various sources put the number of remotely conscious decisions made by an adult to be around 35,000. Okay, so that is a lot of decision made with or without your awareness, right? I mean, if you really need to pinpoint it, you may think of, okay, what to eat, maybe what to purchase, what to browse on the internet, when to do homework, right? And who to spend time with, etc., etc. Okay. And with all these decisions to make, of course, there are big ones, there are small ones, there are more routine ones, there are more sort of one-off ones. But how do you make all these decisions better every day, right? How do you make better decisions or even better optimal decisions every day? And that is really the topic of today's talk, okay? Now, so operations research, where does the name come from? And well, where does it start? At least in China, that is motivated by wartime applications. The Chinese term for operations research actually come as early as the Han Dynasty, which is around 2,000 years ago. All right. It is talking about, for example, disposition of troops, movement of supplies that is related to logistics, right? And also battle plans, management of forces. And all of this are related to decision making. And of course, this is life or death matter, right? You position your troops properly, then you will win the battle. If you didn't, then you get ambushed and you lose the battle, right? It is of high significance. Now, in the very early days of OR, as you can imagine, 2,000 years ago, we don't have that good math, and also we, of course, don't have computers. How do you make decisions? How do people make decisions? Those are basically by rules of thumb, right, and experience. That is why people who, for example, went into battle for many times, they are getting better at it because of their experience and so on. Now, however, with better experience and without a mathematical formulation or mathematical framework, one can only in general achieve good, but not necessarily optimal decisions. And the difference is very fine in some sense, all right? In today's language, for example, let's say you want to walk from your home to the supermarket that is near you, right? And there may be multiple routes to walk to the supermarket, and you find a good route, meaning it is short and doesn't take so much time. And you know it is a good route. But do you know whether it is the best route? Best, for example, in terms of shortest distance, right? Now, if you can find another route that is shorter, then you know that your current route is not the optimal one, not the best one. However, if you are already using the best route, then you cannot find a better one. And so how do you certify or how do you prove to others this is the best route you can take, right? So this creates an interesting mathematical question, and that is how do I find the best and how do I certify it is the best? Okay, so these are the two related questions, and this calls for a mathematical study of decision making. And that is why we want to address this question. So I don't just want to have a good route to the supermarket. I want the best. But first of all, how do I find it? And second, how do I certify this is the best. Okay, so this is something to keep in mind, and this is related to the field of optimization. Okay, so we will come to this. Now, fast forward, so far we have been talking about 2,000 years ago and so on, but fast forward to the early 20th century. And after the Industrial Revolution and the building up of production capacities, so every country faces basically large-scale economic planning and resource allocation problems. This includes industrial production, right? For example, how about I produce, how much steel should I produce, for example, how much other material I should produce, transportation, agriculture, and defense. And of course, all these will have huge impact on various aspects of the welfare of the population, social welfare, politics, economy, and national security, okay? And these problems are becoming very large scale. As you can imagine, you are trying to serve a whole city and you want to allocate resources to each aspect, right? You do not want to produce, for example, all steel, right? And then there is nothing to eat, right? So that is no good. But also, you don't just want to produce food, right? What if the neighboring country come and take your land? That is also not good. So you need to have some industrial production. And how do you trade off the resource you have, and how do you make the optimal planning? That is, of course, of utmost importance. So in the early days, when this field started to take on a more scientific flavor, so in the East, back then is the Soviet Union. So they are motivated by questions of fulfilling production quota, or even over fulfilling the production quota. And so, for example, in one of these problems, one is faced with the problem of maximizing the output of a given product mix from some peeling machines and 5 different materials. And there is a constraint, so each material should make up a certain percentage. And this is in a particular wood factory. And so the Soviet mathematician Kantorovich formulated this problem back then and solve it. So in 1939, and so giving rise to one of the first mathematical approaches to optimal planning problems. Okay. Now, in the West, the philosophy is a little bit different. They are more motivated by notions of price and cost. They want to minimize the price rather than maximizing the output. So for example, during World War II, one of the important questions is about fleet assignment. So I want to assign ships to convoys so as to accomplish a certain delivery of supplies, but I do not want my ship to be empty a lot of the time, right? So I don't want it to travel in ballast for a lot of the time. So I want to minimize so-called downtime of the ship, okay? And this problem, again, is approached from a mathematical point of view by the Dutch economist Koopmans, and he also solved this problem. So, so in the East and in the West, they face similar planning problems. And so in the 30s and the early 40s, people started to look at how to use mathematical techniques to solve this kind of problems. And so what techniques do they use, right? And that is the so-called linear programming, okay? Some of you may have heard about it. You may have learned it in your high school curriculum. May I see a show of hand if some of you have already seen this before? Yeah, so there are quite a number of you have seen it, right? And so this is a very powerful model. And so since a lot of you have seen it, so let me briefly explain the background of this, right? So basically, let us take a look at for example, the production problem, right? The wood factory problem. And suppose I want to produce 2 types of material. One is called pine and one is called oak, okay? And so X is the number of units of pine, Y is the number of units of oak I want to produce. And my function to optimize, that may represent my profit or my utility or my satisfaction, right? And it is given by X plus 3y, okay? Now, so as you can see, X plus 3y will get as big as you want if X and Y are as big as you want. But of course, in reality, you are constrained by resources. And so you can only pick X and Y from this polygon, right? And this represents your production capacity. But then within this polygon represents all the possible combinations of units of pine and oak you can produce. And so you want to pick one that basically maximizes your utility function, okay? And so for those of you who have seen this, then you will notice that since the bigger the X and Y, the better. So you will want to move in the northeast direction in this picture. So that northeast direction is where X and Y simultaneously get bigger. And until you are about to leave this polygon, right? And so you stay feasible, meaning you are still within your production capacity, but you are maximizing your satisfaction, okay? And so some of you may have also known how to do this by hand. And in fact, for Kantorovich and Koopmans, back then there is no computer. They have to solve it by hand. And so it may be large, but of course they also have a team of scientists to help them. And so, but in 2D, basically the picture looks like this. And ultimately you find this red point as the optimal combination. And this is the best you can do, because moving further, then you will leave this polygonal region, and then you are no longer within your capacity. You are exceeding your capacity, okay? Now, this method is okay if the dimension is low, meaning you are only producing two things here, so that you have X and Y, right? But modern production seldom involves only two products, right? So it, of course, involves way more products. And if each product represents one dimension, then you are in trouble, right? Using this method, because from 3D, you have already like something like this, right? And if you have four things to produce, then the problem should sit in 4 dimensions. And that is beyond visualization, right? I don't think many of us can visualize what a 4-dimensional space looks like, right? We have difficulty sometimes drawing a 3-dimensional picture, not to mention 4, 5, up to 10, or even hundreds of dimensions. So what do you need in order to solve this problem? If I really want this to be practical, right, then I basically need algorithms. I need something that is that I can automate and I can implement it in algorithm, in the computer. And so here comes another scientist called Danzig. And back then, he is a mathematical advisor in the US Air Force, helping them to do planning problems. And he developed an algorithm for linear programming in 1947. The algorithm idea is rather simple if you look at the picture. Basically, it looks for the corners of the polygon, right? And a more fancy mathematical term for it is called a vertex, but you can think of it as the corners of the polygon. And by using a smart way to search for the corner, then you can reach the best point in a number of steps, okay? And so this is the algorithm, and he called it the simplex algorithm. Now, the simplex algorithm actually was developed at roughly at the same time as the first electronic computers. So the first electronic computers appear around in the early 40s. And so with this computer and with this algorithm, you can solve a lot of planning problems, very large scale planning problems in an automated way. And so it is fast. And so with this has huge economic and, of course, back then, military advantage. And so here are the 3 pioneers, so to speak, of linear programming, Koopmans, Kantorovich, and the middle is Danzig. Now, these 3, 2 of them won the Nobel Prize in Economics in '75, and that is Koopmans and Kantorovich. Unfortunately, Danzig didn't get the prize at the same time. And apparently, algorithms to the committee is not something that is very a very big breakthrough back then. And so it is an unfortunate thing in history that even though Danzig's contribution is very large, he didn't receive the Nobel Prize in Economics with these 2 other scientists. Now, so what is the first large-scale application of this linear programming algorithm? Okay, the simplex algorithm. And the first one is actually a major international incident in 1948. Back then, basically, as you know, 48 is right after World War II. and Germany was divided into West and East Germany. And back then, East Germany was controlled by the Soviets, and the West Germany was controlled by British, French, and the Americans. But as you can notice in this spot here, this is a city, which is today's Berlin. And back then, Berlin was the capital. And so it got divided into West and East Berlin as well. But as you can see, the entire Berlin city is within East Germany. And so the Soviets want to take over West Berlin as well. And so they block all the roads and rivers to Berlin, to West Berlin, and start a blockade, okay? And to the Western allies, the question then is, do you give up West Berlin? Or then, if not, you will need to think about how to resupply West Berlin, which is a city with around 2 million people back then. Okay, so it is not a simple logistical problem. It is a huge logistical problem, right? 2 million people. So what they devised is an airlift, which is the famous Berlin airlift. So it lasts from 1948 to 49, roughly a year. It is a gigantic airlift. At its peak, roughly a plane landed in every 30 seconds, okay? And so it is a major operation, huge logistical demands on air traffic control, on the material you ship in, and so on and so forth. And so actually, a part of these operations can be formulated as a linear programming problem, and then solved by the newly developed simplex method proposed by Danzig. And so here is a simplified version of the problem. Suppose you have large and small planes. Large planes need more crews, small ones need less crews, and there is an operating cost and cargo hold in terms of the volume. And of course, you want to maximize the volume of cargo transported subject to budget constraints. And so here is one formulation of the problem, which is of course a toy formulation, but still it gives you a flavor of what kind of problems are faced by the planners back then. So at the end, this method is quite successful, and the Western allies prevailed. The Soviet Union withdrew the blockade at the end because it was not successful. Now, after World War II, of course, linear programming and also operation research techniques have more other civilian, more peaceful applications, and it relies heavily on analytical and computational methods for optimal decision making. So that is why I mentioned STEM is heavily involved in operations research. Now, how common is linear programming today? In fact, it is so common that it can be solved by your Excel solve. Okay, so it is used, for example, by most of the Fortune 500 companies, and it is of much relevance and plenty of opportunities. So let me just quickly run through several applications that are more practical to our daily lives. For example, game theory. This is a very simple game. Consider a penalty kick, right? So the striker versus the goalie. So let us, for simplicity, say the striker can choose either left or right. The goalie can choose to dive left or right. And so it is a game, right? So the striker would need to pick a direction to kick, and the goalie would need to pick a direction to dive. And how do you find a good strategy for this, right? Actually, this can be formulated as a linear program. Without this mathematical formulation, it is very hard to reason about this problem because you will need to think about what the other person thinks I think, what he thinks I'm going to do, right? And there is this loop there. E-commerce, right? So when you go online shopping, they have analytics to predict the items that are of interest to you. Back in the back end, it is again some decision making techniques based on operations research to help you do this. Rail scheduling. So in your countries, the rail network is highly efficient. That is because of some planning, and that again is a major operations research problem. Recently, of course, we are in this COVID-19 outbreak, and so public health, of course, require a lot of planning. So for example, where do you set up the temporary hospitals? So it should be accessible. but it shouldn't pass through other heavily populated areas for fear of the contagious disease and so on, right? So you need to optimize the location, optimize the mix of aid material and so on. And this actually, again, plays a big part in planning disaster relief for public health. So going back to our 35,000 decisions, this I will conclude. Basically, many of our daily decisions can indeed be modeled and solved by linear programming, some of which I haven't mentioned explicitly, but for example, shortest path, optimal nutrition intake. You can design your own menu, which basically give you the optimal nutrition intake. Whether that is tasty or not is another question, but at least from a nutrition point of view, it is nutritious. Optimal assignment, currency arbitrage, and so on. And there are still more that can be handled, but then it may not be able to handle by linear programming, but other more sophisticated tools from operations research. Okay. Now, so I hope this very short introduction tells you about the field of decision making and the math and the computational techniques that go behind it, and also its connection to your daily lives. Okay. So I will stop here. Let us start, and with the time we have now, I will briefly introduce our faculty. As you see, our faculty has, here, a number of programs. I won't introduce them one by one, but I will just quickly go over them. But before that, what is engineering, right? And how does it differ from science? And so here is Einstein, how Einstein put it, right? Scientists investigate which already is. So it is related to understanding natural phenomenon, trying to understand what is already there. But engineers create that which has never been, right? A key part of our profession is to create new things. Either it is a software or it is a hardware, which could help in our daily lives. So our faculty basically has 11 programs. So this is a summary of all the programs. So first of all, we have 6 programs that is under our broad-based engineering. So in this case, if you are interested in any of these 6 programs, computer engineering, computer science, information engineering, mathematics and information engineering, mechanical and automation engineering, and systems engineering and engineering management, when you apply, you will apply to our broad-based engineering. And what that means is in the first year, you don't need to choose any one of these 6. You will go through a foundation year, and at the end of the first year, then you will indicate your preference on which one you want to go into. And so you can go into one of these 6, okay? Now, however, we also have 5 programs which have independent admission channels, meaning you can apply to them directly, okay? And here they are, the Artificial Intelligence Systems and Technologies. This is one program. Biomedical Engineering, Electronic Engineering, Energy and Environmental Engineering, and Financial Technology. Okay, so these 5 you can apply directly. And I should caution you that, once you pick one, and if you get into, let's say, biomedical engineering, and if you, within your first year, you decide to, you change your mind and want to get into computer science, you will need to go through a change of major process at the end of the first year. And it is not entirely straightforward, but it can be done, okay? This is the structure of the programs in our faculty, okay? Now, so here are some of the recent achievements of our faculty. Our robotics team is just a crowned champion in a recent Asia Pacific Robocon contest. We are basically competing with all the teams from all the universities around the region, and we got the champion last year. And actually, we have tried many years, and they are a very high-spirited team, and it's a lot of fun talking to them and working with them. Another one is that we also, our programming team won a bronze medal in the 43rd ACM ICPC, the International Collegiate Programming Contest. So this is also a very prestigious contest. Many teams around the world. more than 50,000 students worldwide, more than 3,000 universities, and over 400 on-site competition. And so we won a bronze medal in this. So here they are. Again, they have a long tradition. Basically, every year, those who go before them would train them, and then they will go on to the programming contest. And this is the tradition. We actually encourage our students not just have classroom experiences, but also to go out and compete and put their skills at work, right? And that is important, of course, for engineering. For telecommunications, we are ranked by Thomson Reuters as one of the 10 research institutions in the world with the most impact on telecommunications. And we are also very innovative in the sense that we launched the first Bachelor of Engineering programs in both AI, artificial intelligence, and FinTech, financial technology. And so these are the two programs. AI, we just started last year, and FinTech, we started 3 to 4 years ago. Our faculty is also embracing very diverse cultures. Every year, around 10%, which amounts to around 60 to 70 students. They come from different countries and regions worldwide. And here is just a sample of the countries or regions that they come from. And so we have a very diverse student body in terms of culture, and we embrace the different cultures. So for more information, you're welcome to scan the QR codes as shown on the screen, and you can learn more about the individual programs. And of course, we will be answering your questions here as well. Okay, so thank you all.